Okay, so today we're going to deal with some more of the limits algebraically or analytically, and specifically we're going to be dealing with the type that do not direct evaluate. Remember, direct evaluate, which we did in the last video, means you just plug it in, and then if you get a numerical answer, well, you're done. That's your answer. But sometimes you're going to plug in, and you'll get something like 0 over 0, or you'll get something like infinity over infinity. We'll deal with these really more in a following video, but these are what we call indeterminate forms. Again, indeterminate doesn't mean does not exist. It means we cannot determine what the answer is or if it exists. So if I plug into a limit and I get one of these two issues, we're going to have to do something in order to figure out what the answer is. That answer may end up being does not exist, or it could end up being some easy, nice number, but we have to do something. And so we're going to learn a couple of algebraic kind of strategies and techniques that are going to help us skirt around these indeterminate forms. That's what we're focusing on with this video. Alright, so the first one, let's go for it. We have a rational function. If I were to direct evaluate, so if I were to plug in the negative 3, let's see, you'd have 9 minus 3 minus 6. So you would get a 0 on the top, and then if you plugged in a negative 3 on the bottom, you would get a 0 over in the denominator. Right? So that one, if we were to plug it in, you would get the 0 over 0 indeterminate form, which is a little bit annoying, but this one's not going to be too bad, right? We know whenever we see a rational, we're probably going to want to factor it. So let's go ahead and factor it. Now be careful, do not drop your limit notation until you end up evaluating it. Once you plug in all the x's as negative 3's, right, once you evaluate it, then you could go through and drop the limit notation, but until that evaluation step, you need to go ahead and carry that notation. Let's see, the top I think is going to factor x plus 3, x minus 2, and then the denominator is x plus 3. You can always check by multiplying it back together. That would be x squared. Then you have a negative 2x plus 3, negative 2 plus 3. That does combine to give you the correct middle term. And then the constants multiply to the negative 6. That's wonderful. Okay, so we factored it, and then look, we have this chunk that's present in both the numerator and the denominator, which is going to reduce. Of course, if I'm giving you a question where it's going to be one of these indeterminate issues, and if you think the strategy is to factor and reduce, well, then it's going to reduce, right? You should factor it in a way so that one of the chunks in the numerator matches one of the chunks in the denominator, right? Because if those didn't match, you would still be stuck and you wouldn't have gotten anywhere. So a little bit of common sense kind of helps you keep on track with these questions. So those things reduce. Remember, when you have a rational function and something reduces, you really have a hole in that graph at that point. And then here, this rational function is going to look very, very, very similar to this line, x minus 2. There's just one point where it's different, right? 99.99999% of these two graphs are the same. There's just one thing extra in the rational that's different than the line. And that is, the rational is going to have a hole, right? Since this factor reduces, you're going to have a hole at x equals negative 3. But going back to what we talked about a little while ago, we know that this hole, the discontinuity, that doesn't actually affect the limit. So even though these two functions are not the same, the limits of those two functions will be the same. The fact that that point is missing at that instantaneous value isn't going to change the behavior as we get closer to that value, right? So the hole doesn't affect the limit. That's the long story short. Anyways, once you factor it and once you reduce it, now you're ready to plug it in, right? So now I can change all my x's to negative 3. Now notice, when you evaluate, I'm no longer writing the limit notation. Once I evaluate the limit and plug it in, then you drop that notation, and then you're done, and you should have your answer. Right? So factor and reduce. That's your first strategy. Very common, hopefully not too challenging. The next two, let me scroll it up, yep. The next two, the ones that involve a radical and then a number, the strategy here is going to be to use something called the conjugate, right? Hopefully you remember what conjugate means, but anytime you have a radical and then plus or minus a number, or vice versa, you're going to want to use the conjugate. That conjugate ends up helping us, and something will end up reducing because of it. So let's look at this first example. I have the square root of x minus 3 minus 1 over x minus 4. Let's try to direct evaluate it, because you should always try to plug it in, and if you plug it in and it works, you don't have to do any of this funny stuff. But if you plug it in and you get one of your issues, you have to do something. Let's see, if I plug in 4, 4 minus 3 would be 1. Square root of 1 is 1. 1 minus 1. Okay, so if I were to plug it in, I'd get a 0 on the top, and then 4 minus 4, you get a 0 on the bottom. Okay, all of the questions on this page are going to end up being 0 over 0. I'm probably going to stop testing them because I've done these notes like many times. But whenever you're working on a homework question, or if you're working on a quiz or a test, you should always try to evaluate it and see if you get an answer. But I just know today we're going to keep hitting this 0 over 0 roadblock. So I'm just going to save the time and not keep doing it. Okay, so my strategy is going to be take this original expression, right? Take my function, and I'm going to multiply by the conjugate. Really, we're going to multiply by 1, because there's only two things in math you can do that don't change the value of an expression. You could add 0, that doesn't change the value of your term, or you could multiply by 1. So here we're going to multiply by 1, it's just a very strange 1. We're going to use the conjugate of the radical term, right? The conjugate of the denominator would be x plus 4, but if I did x plus 4 and x plus 4, multiplying by that wouldn't help you. You need to use the conjugate of the uglier term, all right? So let's go for it. I have the square root of x minus 3 plus 1. Conjugate means the first part is the same, the last part is the same, the only thing that's different is the operator. Instead of a minus, it would be a plus. Or if this was a plus, then it would change to be a minus. So the two chunks are the same, it's just the operator that's different. And then you need to do the same thing to the denominator. You don't do this guy's conjugate to the top and then this is denominator on the bottom. You need to do the same thing on the top and on the bottom to keep this equation balanced, right? That's multiplying by a very weird looking 1, but mathematically that is fine to do. Okay, now you see here when we have my original and I'm going to multiply it by the conjugate, here the top are the conjugate pairs, right? This and this are actually conjugates of each other. And whenever you have this trick, when you're multiplying by the conjugates, the level that includes the conjugates, which in this question is the numerator at the top, you're actually going to multiply out those conjugates. But the two things that are not conjugates, which in this case is the denominator, right? X minus 4, this chunk, and then this chunk, those have no relation to each other. Those are not conjugates. So since those two are not related, you're actually just going to leave them factored. Okay, so don't really think about it as being, oh, I'm going to multiply out the top and I'm going to leave the bottom factored. No, top and bottom doesn't matter. What matters is the relationship between the two terms. The two things that are not conjugates, whether they're in the bottom, like this question, or maybe this could have been reciprocated and they may be in the top. But the two things that are not conjugates, you must leave them factored. The two things that are conjugates, you must multiply them out. Top and bottom's irrelevant. It's whether they're conjugates or not. Okay, so let's go for it. Here we're going to multiply this out, so just like FOIL, you do first, outside, inside, last, or if you want to distribute, that's the same thing. But here we go. I've got the square root of x minus 3 times the square root of x minus 3. Well, the square root of something times that exact same square root of something, the square roots are just going to cancel, leaving me the term inside, which is x minus 3. Then I'm going to have plus 1 roots of x minus 3 minus 1 roots of x minus 3, right? The first, the square root's canceled, the outside, inside, and then the last, which is just your minus 1. So we multiply out the conjugates, I leave the non-conjugates factored. And now what's really nice, like why do we use the conjugate, is because these middle two terms, right, you have a plus root and then you have a minus root. Those middle two terms are going to cancel. And that will always, always, always happen when you multiply out conjugates. And now let's regroup what we have. I have x minus 3 minus 1. So here, copy my limit notation. In the numerator, x minus 3 minus 1, that's the same thing as x minus 4. And then I still have this denominator, which I haven't done anything to it yet. And now you should hopefully notice that the top didn't initially look like it was going to cancel, but once those middle two terms reduce and then you kind of combine everything that's left over, now you will have some stuff that reduces. And then you'll be able to evaluate it. Remember, when you reduce with division, it reduces to a 1. So you had to multiply by the conjugate on both layers. The conjugates you actually FOIL out. The non-conjugates you leave factored, and the reason why you leave it factored is because one of those chunks, one of those factors, is going to reduce to the top whenever you're done with all the algebra in the top. Right, so I multiplied by the conjugate, did all the algebra. Now we're ready to direct evaluate. We're ready to plug it in. So change all your x's to 4s. You're going to have 1 over square root 4 minus 3 plus 1. Let's see, 4 minus 3 is 1. Square root of 1 is 1. 1 plus 1 is 2. So we get the answer as 1/2. Remember, we got this 0 over 0, which is indeterminate. That doesn't mean does not exist. If you just see this and you put does not exist on every question, you're going to miss a whole lot of points in this class this year. Right? The answer ended up being a pretty nice number. We just couldn't tell what the answer was right away because it was indeterminate. But when I did my little algebraic strategy, I was eventually able to determine what the answer was. You just couldn't right off the bat. That's why they're called indeterminate. Right, the next one is also a conjugate trick. Let's go for it a little bit faster. Don't use this conjugate, which would be 81 plus x. That's not going to help you. I'm going to need to use the uglier conjugate, which would be the root of x plus 9 on the top, and then you got to keep it fair. Do the same thing on the bottom. And then we're going to multiply it out. Remember, the non-conjugates, you're just going to leave them factored. And then the two things that are conjugates, you multiply them out. So we have the root of x times the root of x. That's x. Then you'd have plus 9 roots of x. And then minus 9 roots of x. If you know, like, hey, I'm multiplying conjugates, those two things are going to cancel, you don't have to write them just to cross them off, right? If you just want to skip straight to having this, like, that's perfectly fine. Okay, let's regroup. So I multiplied by the conjugates. Of course, the middle two terms canceled. And then here I can see what I have. Now, does this chunk in the lower left of the denominator, does that match the numerator exactly? No. It's really close, but it doesn't quite match exactly. But what I can do, either from this term in the bottom or from this term in the top, is I can factor out a negative. And then if I factor out a negative from one of the terms, then it's going to end up being the same. I'm going to factor out a negative from the top, just because I think that's a little bit easier to see. So I still have my limit. I haven't plugged in the x value yet. But here I'm going to factor out that negative. Remember, when you factor out a negative, what you're doing is dividing. So if I had an x and I divided it by negative, you'd have negative x. If I had a negative 81, factor out the negative. So whenever I factor out that negative, then that chunk in the numerator is going to end up matching that chunk that was in the denominator. You could have easily have left the top the same and then factored out the negative from that chunk in the bottom, and then you would have the negative on the bottom, and then those two would have been 81 subtracted from x, right? It doesn't really matter. You're going to factor out the negative from one of the layers. Don't factor it out from both, because then you're going to just basically switch where those two things are. But you just factor the negative out from one of the chunks, then you can reduce it, and then you'll be able to evaluate it. So let's finish this one. You still have the negative on the top. And then I can go ahead and evaluate. So I have negative 1 over, that's 9 plus 9. So we have a negative 1/18. Now, a little note, here we have the square root. That's called the principal square root, right? Since that radical was already in the question, you only wanted the positive value. This right here was 9. If I had something like x squared equals 81, and then in order to solve for x, if I physically take the square root, that's when you would have plus or minus, right? When you perform the action of reducing it from quadratic to linear, that's when you would need the plus or minus. But if the radical is already there for you, it only wants the positive. And again, that's called the principal square root. You only need the plus or minus when you perform the action of reducing it from quadratic to linear, when you take the square root. Alright, so the conjugate trick, probably the one with the most algebra. Well, the next one's going to have some algebra also. But the conjugate trick is the one that students usually struggle with the most. Alright, the next one, you see we have really 3 fractions. I have 2 fractions on the top, and then of course I have the fraction as a whole. Alright, that's way too many fractions. The strategy here is just going to be to combine and simplify. So I'm going to have some little algebra tricks. I hope you pay attention. If you're confused about the tricks, you can always Google it or look it up or just rewatch the video, or you can email me, that's fine. But we're going to have some algebra tricks that make this a little bit faster. If you were to plug this in, you would get 0 over 0. I'm not going to. But what we're going to do first in order to get this algebra done so we can eventually get an answer is we're going to combine these fractions in the numerator, and then we're going to combine the fractions overall, and we're going to shrink this down to just one overall fraction where there's one numerator, one denominator, and then we're going to magically have an answer. But first thing, let's combine the fractions that were in the top, right? So I'm going to leave the denominator the exact same. If you want, you could go through and think about, okay, what's the least common multiple? What can I make this and this both into? Multiply this by 2 over 2, multiply this by x plus 2 over x plus 2. Right? You could go that route if you want, but I've got a little trick that I like to call fast adding, right? So whenever you're adding or subtracting fractions, you can really combine them very, very, very quickly. Here's how it goes, right? We're going to combine these two into just one fraction. Here's the trick. You do diagonal, right? You basically cross multiply to get the stuff in the top. So I'm going to do 1 times 2. And then I'm going to do the other diagonal. So x plus 2 and then 1. And then whatever the operator was, you just keep it the same. Right? So I'm going to cross multiply to get the top. Right? This diagonal gave me this chunk. This diagonal gave me that chunk, keeping the operator the same. And then in order to get this denominator, I'm just going to take these two denominators and multiply together. So I'd have x plus 2 times 2. So that's a fast adding trick, right? You can look it up if you want, but it's going to always work whenever I have an adding or a subtraction between two fractions. Cross multiply to get the top, and then multiply across to get the bottom. It's going to work 100% of the time, every single time. It's faster than finding the least common multiple, multiplying the left side by one chunk, multiplying the right side by the other chunk, and then adding them together. The fast adding trick is doing all of that same work. You're just kind of doing it in your head and with a little shortcut. It's a good trick. All right, let's distribute this negative. So I've got still the denominator. I'm going to leave it as x. Let's see. Here I'm just going to have 2 x plus 2, I'm going to leave that denominator as it is for now. Let's just distribute this negative. So I'm going to have 2 minus x minus 2. So 2 minus x minus 2. And then the 2's are going to end up canceling. Okay, so I've combined all those fractions in the top with my fast adding trick. Now what I'm going to do is I'm going to change that denominator so that it also looks like a fraction. But now what I'm going to do is I'm going to combine this kind of complex fraction. Instead of having a fraction in the top and a fraction on the bottom, I'm going to compress that down to just one fraction overall. And I like to think about this as something called the sandwich trick, right? You see you've got a little sandwich. You've got a 4-layer sandwich. You've got the top, and you have these middle two, then you have the bottom. You could take this, rewrite it over here, and then multiply by the reciprocal, right? The trick that I'm about to do is going to accomplish that exact same math. You're just doing it without writing it all out, right? Here I'm going to copy my limit notation. In order to do this division with fractions, if you want to skip the steps of multiplying by the reciprocal, you just need to remember this sandwich trick. The middle 2 layers are going to multiply together, and then they go to the bottom. So these 2 layers multiply, they go to the bottom. The outside 2 layers, they're going to multiply, and they're going to go to the top. It's literally the exact same thing as taking this, flipping it, and then just multiplying by the reciprocal. But you can do all of that math without writing it, right? Middle 2 go to the bottom, outside 2 go to the top. So we have those 2 tricks with the fractions. The sandwich trick, which works, or sorry, not the sandwich trick, the fast adding trick, which is how you can add or subtract fractions very, very, very quickly, where you cross multiply to get the top, multiply across to get the bottom. It's always going to work when you have 2 fractions. Can't do it if you have multiple, but 2 fractions is fine. And then you have the sandwich trick, middle 2, multiply to the bottom, outside 2, multiply to the top, right? That makes this algebra go a lot faster. Now finally I've got it down to just 1 layer, right? 1 fraction overall, and I can see I've got an x that's going to reduce. So let's regroup everything that we have. X is going to 0. I've got a negative 1 on the top, 2, x plus 2 on the bottom. So I did all the algebra to compress all those fractions, get it down to just 1 overall, and now we can evaluate it. 0 plus 2 is 2, 2 times 2 is 4, so then this answer ends up being negative 1/4. Okay, last 2 on this page are going to be some more factorizations. So these are also going to be factor and reduce, just like the first one on this page, but this is going to involve either the sum or the difference of 2 cubes. Right, so let's do a little bit of review. If I had something like x squared minus 81, you know that would factor x plus 9, x minus 9. Or if I had something like x squared minus 25, you know that would be x plus 5, x minus 5, right? We know how to factor stuff like that. That's called the difference of 2 squares, dots, right? Difference of 2 squares. Difference means subtraction. 2 squares means that's a perfect square, that's a perfect square. So we know the difference of 2 squares factors into those conjugates. We like those. Those are really nice. By the way, there's no such thing as the sum of 2 squares, right? If you tried to factor this, it doesn't work, right? That ends up giving you imaginary solutions. So the sum of 2 squares is not a thing, but the difference of 2 squares is very much a thing. And you should know how to factor stuff like that. You may even remember the name difference of 2 squares, or dots. The difference of 2 squares factors into conjugates. And here, the sum and the difference of 2 cubes is also going to follow a pattern. And this one's nice because here the addition and the subtraction both work. In general, for your difference of 2 squares, if I had x squared minus a squared, it would factor x minus a, x plus a, right? Or you could flip them, right? The order for the multiplication doesn't matter. But notice, I'm working with the roots. I'm working with the smaller numbers when I factored. Like when I had something like this, you had x minus 9, x plus 9, right? You didn't have 81s over here. You had the root of 81 over here. And you didn't have x squareds in the factorization. You had the square root of x squared, right? So when you factor it, remember, you have the smaller terms. You have the roots. You don't use the bigger things. So the same thing is going to be true when I have the sum or the difference of 2 cubes. When you factor it, you're going to be working with a and b, right? Not with the a cubed and not with the b cubed. All right, let's go for it. Both of these are going to follow the same pattern. It's going to be a binomial, which means 2 terms, and then a trinomial, which is 3. All right, so let's go for it. The cube root of a cubed is a. The cube root of b cubed is b. So those are the numbers, those are the values that we're going to end up putting in here. And then here's the pattern. For the binomial, you need an a and a b. For the trinomial, you need a times a, which is a squared. Then you need a times b, which is ab. And then you need b times b. So for the binomial, you need one of each. And then for the trinomial, a times b, b times b, right? That's the form for how it factors. And the difference of 2 cubes is going to follow the exact same thing, right? You're going to have a, b, a, b, b, right? And then what's going to be different is the operators that we put in, right? There's 3 spaces, right here between the a and the b, right here between the a squared and the ab, and then here between the ab and the b squared. There's 3 places where we're going to put an operator, either a plus or the minus. And how we can remember what operator goes there, there's a nice little rule called SOAP. Right? It's kind of a little bit weird, but it actually helps you remember it. SOAP is going to stand for same, opposite, and then always positive. Oops. So SOAP for the signs. Same, opposite, always positive. So when I'm factoring either a sum or a difference of 2 cubes, you have to identify what the cube roots are. Then you can put those terms in, right? A, B, A, B, B, B. And then it's SOAP for the signs. So let's check it out. This first one, the sum, it was a plus. So this first operator is going to be the same. So if it was a plus, this operator is the same. The second operator is going to be the opposite. And then the third one's always positive, right? So same, opposite, always positive. And that's in relation to the operator that it began with. Now for the difference, you'd have same, opposite, always positive. That is how you can factor the sum or the difference of 2 cubes pretty quickly. Shouldn't be too bad. I'm sure you were taught it at some point in the past. You just probably forgot it. Anyways, let's use this information to answer these last 2, and then we'll flip it over to the next page. All right, this would be 0 over 0 if you plugged it in. So let's factor it. The bottom, I'm just going to leave x minus 3. This is a difference of 2 cubes. I know the cube root of x cubed is x. And the cube root of 27 is 3, right? 3 to the 3rd power. 3 times 3 times 3, that's 27. So my roots are 3 and x. So let's use this to fill it in, right? So I'm going to have x, 3, I'm following a, b, a squared, a, b, b squared. So x, 3, then I need x times x times 3, and then 3 times 3. Right, so once you identify the roots, it's pretty easy to fill in what those values are. And then I need SOAP for the signs. Same, opposite, always positive. And look at that. That binomial ended up matching the term we had in the denominator. It's almost as if someone planned it that way, right? Like, of course it's going to reduce, because if it didn't reduce, you would still be hitting that 0 over 0 issue, and you'd still be stuck. If you think it's going to factor, it had better factor in a way that's convenient and helps you solve the question, right? If it factors and it doesn't give you an answer, well, that would just be a very mean question. I wouldn't do that to you, right? So, of course, you look at the denominator, and it kind of tips you off what the binomial has to be, but you should still follow the rule and make sure that you're getting the right algebra as a result. All right, so here we got x squared plus 3x plus 9. That's what's left. Once I factor and reduce, now I can evaluate it. 3 squared is 9. 3 times 3 is 9. 9 is also 9. So then we get the answer is 27. right? So the sum and the difference of two cubes, some extra factorizations, but you should know those going forward. Last one, and then I'll probably just break and we'll do the next page on a different video. Let's factor it. Here, the denominator, I can factor. That's a difference of two squares. So that's going to factor x plus 4, x minus 4, right? It factors into conjugates. And then here I've got the sum of two cubes. So the cube root of x cubed is x. The cube root of 64 is 4. So this is going to factor into a binomial and a trinomial. X for x times x, x times 4, and then your 4 times 4. And then you need SOAP for the signs. So same, opposite, always positive. So factor, and then one of those two chunks had better reduce, which in this case, it's going to be the x plus 4 chunk. You could try to factor the top farther, but it's rarely ever going to go any farther, right? Typically, this is just a quadratic that doesn't factor, right? It's not going to have two more nice roots for you. So you could try to spin your wheels and try to get that numerator factored, but you're most of the time just going to be wasting your energy because typically that does not factor any farther. But that's okay, right? I factored and reduced, so now I'm going to try to evaluate it. Remember, I would have evaluated it at the first, but you would have gotten 0 over 0, so that's a problem. You have to do something. But after I factor and after I have that chunk that reduces, now let's go ahead and try to reevaluate it. So let's plug in the x values as negative 4. So I'd have negative 4, or I'll just write it, negative 4 squared minus 4 times negative 4 plus 16. Then you have your negative 4 minus 4. Okay, that's going to be a positive 16. Negative times negative, that's also going to be a positive 16. That's also a positive 16. Then negative 4 minus 4, that's a negative 8. 16 times 3 is 48. And then 48 divided by negative 8 would be negative 6. Okay, so let's recap these strategies that we had today. Factor and reduce, probably the most common and probably the easiest of the strategies. If you see something and you direct evaluate it and it gets you one of these two indeterminate forms, it doesn't mean does not exist. It doesn't mean there is no answer. It means I cannot determine what the answer is by simply plugging in. But if I do some little technique or some little strategy, then you will be able to find the answer, right? And the first strategy was to factor and reduce. The second strategy is to use the conjugate. And then another strategy, if you have multiple fractions, is just to combine them all, condense them down into just one fraction. Oh, okay, we're back. I totally forgot there was another page before we get to the trig ones. So let's go ahead and do the examples on this page too in the same video. And then we'll break and we'll do the trig in the next video. Right, so here, these are also going to be, let's just tinker around with some of the algebra, and then let's go ahead and see if we can use the algebra to get the answer. So here, it's just do some algebra first, and then see if anything reduces or cancels. Right, this is a little bit weirder because you've got delta x going to 0. So anywhere you see a delta x, you would just plug in 0. So you'd have, basically, that would cancel and that would cancel. So you'd have 3x minus 3x. So you would get a 0 over 0 if you tried to plug it in. But we're going to be able to do this if we distribute first. All right, so let's look at this one. Delta x is going to 0. Let's distribute the 3. So I have 3x plus 3 delta x minus 3x. 3x's are going to cancel. Then I have 3 delta x over delta x. Now here the delta x's cancel. And I have just the limit as delta x goes to 0 of 3. Well, this means, right, I know it's a little bit weird to have delta x. This means, though, anywhere you see a delta x in my expression, I would change all of those delta x's to 0. But there are no delta x's, right? That's just a constant. And we know the limit of a constant just is that constant, right? And here you wouldn't plug in the x as 0. You plug in the delta x as 0. Remember, this thing underneath the limit, that tells you what to plug in and which variable to plug it in for. So here, direct evaluate didn't work. But if I do the algebra first by distributing, then you end up getting an answer. Next one, if we FOIL this guy out, if you tried to evaluate it, you would get the 0 over 0 again. I'm not going to check it, right? If you want to, you can do it, but I'm not. But if we FOIL this sucker out and then do some algebra, we will get an answer. So here, multiplied out, you'd have x squared minus 10x plus 25. That's what you would get if you multiplied this out. Then I have the minus 25 over the x. So let's see, the 25s are going to cancel. And then if you could reduce everything here by an x, right? You could factor out an x on the top if you want, and then cancel it. Or if you can see how all of this has at least one x, and that you can just visually reduce it without having to write it out, that's fine. But when you reduce it, you're going to have an x minus 10 left. Then you can evaluate it by plugging it in. 0 minus 10 is negative 10. So if you just multiply it out, then cancel and reduce, you will get to the answer. These next couple, it's really just going to be in your best interest to use the graph. There's not really an algebraic strategy for doing it, but if I look at these and I have some weird answer and I'm not feeling like I'm getting something valid at the beginning, you could always just use the graph, right? We know we could use a table or we could use a graph to answer limit questions. So if the algebraic just doesn't seem possible for us, use one of your two other methods. So let's sketch this. You see it has an asymptote at 3. The horizontal asymptote would be at 0. And then there's no x-intercepts. And then if you were to test some points, you'd end up seeing that this graph. Let's see, if I got the y-intercept, it's going to be at negative 1/3. So the y-intercept is here. So this graph is going to look more or less like this, right? You have your vertical asymptote at 3, and then you have your horizontal asymptote at 0. It's up in this part, down in this part. Now let's evaluate these limits using the graph. It says, as I approach 3 from the right. Remember, 3 is where my vertical asymptote is. Sorry, kind of off the screen, that's my bad. 3 is where your vertical asymptote is. So if I start on the right side and then I go up, it looks like that limit from the right side is going to end up being a positive infinity. If I were to approach 3 but from the left, remember here's 3, it's your asymptote. If I started on the left side and then came back towards my target, looks like that's going to take you down towards negative infinity. So the limit from the right and the limit from the left are different. That means this overall limit does not exist. And your reason why, I would always, always, always encourage you to write your justification. Your reason why is because your limit from the left doesn't equal your limit from the right. Because of the asymptote. One side goes up, the other side goes down. That asymptote kind of messes stuff up. Now this next example actually looks fairly similar, but notice since the asymptote is squared, right, the top one is always positive, and the bottom, since you have this chunk and it's squared, you know the bottom's always going to be positive. This graph is going to be kind of similar, except instead of existing down here, the graph cannot possibly be negative. So here, since the asymptote is squared, actually both sides are going to end up going up, right? When the asymptote was repeated once, or if it had a multiplicity of 3 or 7 or any odd number, one side would go up, the other side would go down. But if the asymptote has an even multiplicity, both sides are either going to go up or they'll go down, just based on the signs for the rest of the question. Okay, so here we could check from the right side, it goes up, from the left side it goes up, those match. So this overall limit would exist. This one doesn't, because one side goes up, the other goes down. Here, both sides go up, right? So be careful. When you've got the asymptote squared, you should know there is going to be a limit. It may be up, or if that was a negative sign, then they would both be going down. But if the asymptote is squared, you're not going to have one of those janky little situations where one goes up and one goes down. Okay, last three. Here we have k as a constant. Seems a little bit weird. If you want to just, if you think it's hard to work with k's, just change the k's to 4, or change the k's to 3, or just change it. Plug in some number, and then work with the numbers, then try to come back to k's at the end. But really, we can factor this guy, limit as x is approaching k. This is a difference of two squares, so it's going to factor x minus k, x plus k. And then in the denominator, it looks like you can factor out an x. And then after you factor out an x, you'll have an x minus k left over. And then you have that chunk and that chunk, which reduce. And then we can go ahead and evaluate it. So I'm going to change all of my x's to k's. So this x, change it to k. That thing already was a k. This x, change it to a k. So I've got 2k over k, which is 2. Okay, so that one was also factor. It was a little bit weirder because it had a k in there instead of a number plugged in, but you should still be able to get it. And then these last two are also going to be things where, hey, you may just want to use the graph to help yourself get the answer. All right, let's think about what this graph would look like. You've got the absolute value of x minus 5 over x minus 5, right? And anytime you've got the absolute value of stuff over that same stuff, that's your step function. So here, this is just going to be a step function, except it's shifted. Looks like it's shifted 5 units to the right. So 1, 2, 3, 4, 5. The upper step is going to be up at 1. The lower step would be down at -1. Right? So it's your typical step function, right? Except it's just shifted 5 to the right, which is why you have the -5 inside. All right, so let's think. Here it's asking for the limit of the step function as x approaches 5. The limit from the left would be this point, which is -1, right? This left side is taking you towards this location, which is at a height of -1. The limit from the right, you start on the right side, but then come back towards your target. It's taking you towards that point, which is at a height of 1. Those don't match. So this answer does not exist because the limit from the left doesn't equal the limit from the right. Now this last one seems like it's tricky. Like you're like, Mr. Bell, okay, I know what this graph looks like now, but when you throw in the x squared, oh my gosh, like I have no idea what this graph looks like. Well, that's okay, like neither do I, but you don't need to know what this really weird ugly functions graph looks like. What you can do is use some of your limit properties, right? I'm going to split this up. I'm going to take the limit. Notice this is only from the right too, right? It's not an overall because the overall didn't exist. But I could use my limit properties and I could split this up. I'm going to take the limit of x squared, right? You have x squared times this other stuff. I'm going to specifically group it so that I have the x squared times the step function. And then I can just apply the limit to each one. So don't forget about those properties. This one seems like it's hard, but if you remember that, hey, like I could just split it up and I could group it, like x squared, and then you have the step function, and then you could go through and you could answer these questions pretty easily. The limit of x squared, just plug it in, 5 squared is going to be 25. And then the limit of the step function, but only from the right, that limit was 1. So here I can get the answer as 25. Seems like a weirder question because it looked ugly, but remember, you just split it up into groups that you can work with. And if you really wanted to, you could do x times this, and then you could like times 1 over x minus 5. Like, you could split it up really far, but really you just want to split it up just enough into stuff that's convenient to you. Like I wouldn't really advise doing this. That's just make things more complicated. Keep those two terms together because you know you can work with that chunk, right? And you could do 5 times 5, but you could also just leave it as the x squared. Split it up, but split it up into convenient chunks. Okay, that's it for right now. Next time we'll pick up with some special trig limits.